Chemical kinetics. Definition: chemical kinetics deals with the speed or rate of a chemical reaction and the factors affecting this rate. Rate of reaction. Definition: the rate of reaction is the change in concentration of reactants or products per unit time. Formula: text rate, frac text, change in concentration, text time taken. Unit: mole L-1 S-mons. How are factors affecting the rate of reaction? 1. Concentration of reactants. Higher concentration, faster reaction. 2. Temperature. Higher temperature, increased rate due to more energetic collisions. 3. Catalyst. Catalyst speeds up the reaction without being consumed. 4. Surface area. Finely divided solids react faster due to larger surface area. 5. Nature of reactants. Ionic reactions are faster than covalent reactions. 6. Pressure for gases. Increasing pressure increases the rate for gaseous reactions. Instantaneous rate versus average rate. Average rate, rate over a time interval. Instantaneous rate, rate at a particular moment. Important points. Faster reaction means higher rate. Rate decreases as the reaction proceeds because reactants get used up. Units can vary depending on the order of reaction. Would you like me to only? Reaction ka raz, the secret of the reaction. Concept: in a chemical reaction written as text AA, text BB, right, product participates in a fixed ratio known as the stoichiometric coefficient. The small letters A, B, C, D represent the number of moles of each substance involved in the reaction. As the reaction proceeds, the amounts of reactants and products change proportionally according to their coefficients. Expression for related to stoichiometry: fra A, del A equals frac minus delta B, B equals frac delta C, C equals frac delta D, D. Where delta A, delta B equals decrease in concentration of reactants, delta C, delta D equals increase in concentration of products. Negative sign minus shows decrease in reactants. Instantaneous rate versus average rate of reaction. Average rate of reaction. Definition: the rate measured over a finite time interval during the reaction. Formula: text average rate delta text concentration T, where delta T equals time interval. Graph concept: in a concentration versus time graph, the average rate is the slope of the secant line connecting 2 points. Instantaneous rate of reaction. Definition: the rate at a specific instant of time during the reaction. Formula: text instantaneous rate equals lim delta T to 0 delta concentration delta T, or derivative frac reactant dt. Graph concept: in a concentration versus time graph, the instantaneous rate is the slope of the tangent drawn at a particular point. Diagram: imagine concentration versus time graph. Curve slopes downward as concentration decreases. A secant between 2 points shows average rate. A tangent at 1 point shows instantaneous rate. Rate law and specific rate constant. Rate law, or rate equation. Definition: rate law expresses the relationship between the rate of a reaction and the concentration of reactants raised to some powers. General form: text rate equals Ka(x) b squared y, where A equal y's concentrations of reactants stars x does not y, order of reaction with respect to A and B, experimentally determined, not necessarily equal to stoichiometricians. K equals specific rate constant or rate constant. Specific rate constant K. Definition: it is a proportionality constant in the rate law, which is characteristic of the reaction at a given temperature. Important points. Stochastic K depends only on temperature and nature of the reaction. K is independent of the concentration of reactants. Units of K depend on the overall order of the reaction. Important formula: text rate equals K, reactant 1 text order. For a first order reaction, text rate equals Ka. For a second order reaction, text rate equals A2 quad text or quad Kab. Order of reaction and molecularity. Order of reaction. Definition: the order of a reaction is the sum of powers of concentration terms in the rate law expression. Important points. Order is experimentally determined. It can be 0, fractional, or whole number. It is not related to stoichiometric coefficients directly. Example for rate law, ta, rate equals Ka to B1, order equals 2 plus 3, third order reaction. Molecularity of reaction. Definition. Molecularity refers to the number of molecules or species that collide simultaneously to bring about a chemical reaction. Important points. It is always a whole number, 1, 2, or 3, unimolecular, bimolecular, trimolecular. Cannot be zero or fractional. It is theoretical, depends on the reaction mechanism. Types. Unimolecular reaction involves one molecule. Example, text 2, text O5, right arrow text NO2 plus text NO3. Bimolecular reaction involves two molecules. Example, text H2 plus text I arrow 2, 2. Trimolecular reaction involves three molecules, rare due to low probability of simultaneous collision. Difference between order and molecularity. Property, order of reaction, molecularity, molecularities, based on experimental results. Value can be zero, fractional, or integer. Always whole number 1, 2, 3. Depends on rate law, number of colliding species. Changes with conditions, yes. No fix for elementary reaction. Elementary, non-elementary complex reactions. Elementary reaction, a reaction that takes place in a single step. The molecularity and order are usually the same. Example, no, text O3, right arrow text NO2 plus O2. Non-elementary or complex reaction, a reaction that occurs in multiple steps. The overall reaction is the sum of elementary steps. The order is determined by the slowest step, rate determining step, not by stoichiometry. Example, 2 text no 2, right arrow 2 text O no 2, proceeds through multiple steps. Units of rate of reaction and rate constant K. Unit of rate of reaction, always text mol L, -1 text X S1, same for any reaction. Char unit of rate constant K, the unit of K changes depending on the order N ta of reaction. General formula for unit of K, text unit of K equals left mol L squared minus 1, right 1 minus N, it's 1 minus 1, where and its order of reaction. Quick examples. Reaction order N, unit of rate constant K, mol L mess, 0 mol S harm S mess, sur 1 mits S mos 2, L mol minazon S mos 3, L squared mol rate constants types. 1. Rate constant of individual species, defined as individual rate constant divided by its stoichiometric coefficient. 2. Rate constant of overall reaction, defined as common rate constant that applies to the entire reaction. Important, rate constant of reaction is constant for a given temperature. It does not change with concentration. Summary, key points. Rate of reaction unit equals mol L minus mon S moles, always same. Rate constant unit equals depends on order of reaction. K equal constant at constant temperature. Elementary, single step. Complex equals multiple steps. Zero order reaction. Definition, a reaction in which the rate is independent of the concentration of reactants. The rate remains constant throughout the reaction until the reactant is completely consumed. So go rate law for zero order K. Here is the rate constant and it is equal to the rate. Integrated rate law starting with text equal minus a frac d8 dk. On integrating A equals 0 minus kt, where A equals concentration at time t, A equals 0 equals initial concentration, K equals rate constant, T equals time. Relationship between A and B in first order reaction. Given reaction, A right arrow B, BA at any time T, amount of B formed equals text initial amount of A, text amount of A remaining. In concentration terms, B equals A0 minus A, where A0 equals initial concentration of A equals concentration rate law, first order reaction rate, text rate equals Ka, where K equals rate constant, A equals constant is the rate constant, and it is integrated rate law starting with text equal minus a frac d8 dk. On integrating A equals 0 minus kt, where graphical representation, A versus Tia, straight line with negative slope, slope minus K, graph intercept D, P equals A. Graph, y-axis, A, x-axis, T, straight downward line, linear decrease. Units of rate constant for zero order, text unit of K, K equal text mol L minus 1, text squared minus 1. Half-life, TIF for zero order reaction, formula T1 half equals frac A0 2K. Important, half-life depends on initial concentration A0. Half-life T assured for zero order reaction for T50 equals frac A0 to score 2K, meaning half-life is directly proportional to initial concentration A0. Hash general formula for any percent completion T true. Tx equals frac x 100 times frac A to K, where x rise equals percentage of completion, e.g. 25%, 75%. In terms of T50 and Tx frac x 50 times T50. Special cases, T75 equals 1.5 T50, T100 equals 2 times T50. Key features of zero order reaction. Rate does not depend on A. A decreases linearly with time. Common in surface catalyzed reactions. Examples: decomposition of ammonia on platinum surface, photochemical decomposition of HI, clean first order reaction. Definition: a reaction in which the rate is directly proportional to the first power of the concentration of a single reactant. Rate law for first order reaction. Text rate equals Ka. Here, Kate is the rate constant, and A is the concentration of reactant. For integrated rate law, starting from text rate equals frac dAt, on integrating ln A0 minus kt, rearranging A equals A0 equal minus kt, or using log base 10. Log A equals log A0 minus frac kt, 2.303. Graphical representation, straight line with concentration of the perfect. Right equals kt, where A0 equals the concentration at time t. Ka equals rate constant. T equals time. Half-life T source said for first order reaction, formula T50 equal frac 0.693 K or P50 approx for 0.7 K. Important, in first order reactions, half-life is constant, independent of initial concentration, A score 0. Other important time relationships. Time relation with T Sumpert Swart Sero, T Sun 2T50, T Torf Sem point Xer, 3 Sir at 3.C 4T50 frac 10 3T50. Graphical representation, straight line with negative slope, slope neg K. Also a straight line. Y-axis, when A or log A, x-axis, T, linear decrease. Units of rate constant for first order, text unit of K, S squared minus 1. Half-life, T1 half 3 K. T1 equals frac 0.693 K. Important, half-life is independent of initial concentration. Key features of first order reaction. Rate depends linearly on A. Exponential decrease of A over time. Half-life is constant, does not depend on A0. Examples: radioactive decay, hydrolysis of esters in acidic medium, decomposition of N2O5. Pseudo first-order reaction. Definition: a reaction that appears to be of second order bimolecular, but actually behaves like a first-order reaction under special conditions. Why? Because one reactant is present in large excess, its concentration remains almost constant during the reaction. Thus, the reaction depends effectively only on the concentration of one reactant. Key idea: in reality, reaction is bimolecular, two reactants involved. But practically, only one reactant's concentration affects the rate significantly, so the reaction follows first-order kinetics. Example 1. Hydrolysis of sucrose, sugar. Olv, text H22. Text O11 plus text. Water is in large excess. Its concentration glucose text fructose. Sucrose reacts with water in acidic medium. Water is in large excess. Its concentration remains constant. Therefore, rate depends only on sucrose. Thus, the reaction behaves like first order. Example 2. Hydrolysis of ester, text 3, text COOC, text 2 chlorous H5 plus text H axt Q3 COOH, text ester reacts with water to form carboxylic acid and alcohol. Again, water is present in excess, treated as constant. So the reaction becomes pseudo first order. Important condition. One reactant must be in excess to make a second order reaction behave like first order. Quick recap. Actual reaction type, pseudo observed reaction order. Bimolecular, 2 reactants appears unimolecular, 1 reactant. Presence of excess 1 reactant equals pseudo first order behavior. Energy and activation energy. Threshold energy E. Definition. The minimum energy that reactant molecules must have so that they can successfully form products. Important. Without reaching threshold energy, the reaction cannot proceed. Text threshold energy, minimum energy needed for reaction. Activation energy. Definition, the extra energy that must be supplyactant molecules so that their total energy becomes equal to the threshold energy. Activation energy prepares the reactants to cross the energy barrier and form products. Text activation energy equal threshold energy of reactants. Enthalpy change, H, and type of reaction. If delta H is negative, reaction is exothermic, heat is released. If delta H is positive, reaction is endothermic, heat is absorbed. Sign of delta H, type of reaction, negative, exothermic reaction, positive plus, endothermic reaction. And hash, effective catalyst on activation energy. Positive catalyst definition. A catalyst is a substance that increases the rate of reaction by decreasing the activation energy, E. It provides an alternative pathway with lower energy. Thus, molecules reach the threshold energy more easily. Result, faster reaction, lower activation energy. Summary, stats, key points. Threshold energy is minimum energy required. Activation energy is the extra energy needed. Del H negative, exothermic. Del H positive, endothermic. Catacreases activation energy, speeds up reaction. Arrhenius equation and temperature dependence of rate constant. Arrhenius equation. It explains how the rate constant K star depends on temperature T and activation energy E or. Formula. K equals A e to the minus EA by RT, where K equals rate constant A, Arrhenius factor, frequency factor, EA equal activation energy J mar, R equals gas constant 8.314 J mol K, T equals temperature in Kelvin, E equals base of natural logarithm, approx 2.718. Meaning of terms, A Arrhenius factor, frequency of collisions, orientation factor for successful collision, E minus EART, fraction of molecules that have energy activation energy. Higher T, larger fraction, faster reaction. Arrhenius plot graph. When we take logarithm of Arrhenius equation, ln K equals ln A minus frac EAR times frac 1T. This is a straight line equation, y equals mx plus c, where slope equals m of r and intercept a. Important points about the graph. Plot ln K versus 1t, slope equals EAR, negative slope, intercept equal NA. Graph is straight line going downward. Effective temperature on rate constant. If temperature increases, rate constant K increases exponentially. General rule, for every 10 degrees rise in temperature, the rate of reaction doubles, approximately. Summary key points. Arrhenius equation relates K, T, and E psi. A equals frequency plus orientation factor. Higher temperature, lower frac, EA higher T, K. Plot of ln K vs 1T, straight line with negative slope. Collision theory of chemical reactions. Basic idea. For a chemical reaction to occur, reactant molecules must collide with each other, but not every collision leads to a reaction. Only effective collisions result in the formation of products. Conditions for effective collision. 1. Sufficient energy. Colliding molecules must have energy, activation energy, equal. 2. Proper orientation. Molecules must collide in the correct direction, specific orientation. Both energy and orientation must be correct for a successful reaction. Rate of reaction according to collision theory. Rate of reaction, number of effective collisions per second. Effective collision rate, collision frequency, fraction of molecules with energy, quarter E. Factors affecting collision rate. Increase in temperature. Molecules move faster, more collisions, faster reaction. Increase in concentration, more molecules, more collisions. Addition of a catalyst lowers activation energy, more collisions become effective. Summary key points. Only effective collisions with sufficient energy and proper orientation lead to a chemical reaction. Rate of reaction depends on the number of effective collisions. Temperature, concentration, and catalysts affect the rate of reaction.